The prevailing hypothesis among most researchers is that the momentum clarifications regarding the beginnings of the universe remain the main interpretation of its initial development. This speculation connects the production of stars and planets, which ultimately led to the emergence of life, including humans. Despite its uncommon title, the Big Bang Theory provides a comprehensive perspective on what could have happened at the universe's dawn. In the beginning, the universe was concentrated in an incredibly minuscule space, far smaller than the tip of a pin, and packed with particles. From this densely packed state, a massive release of energy and matter, known as the Big Bang, occurred. This catastrophic event, which took place billions of years ago, set into motion the vast history of the universe. As scientific understanding advances, however, discrepancies have begun to emerge, raising doubts about the assumptions of this hypothesis. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space observatory ever built, experts expected its observations to confirm the Big Bang Theory. Yet, within 1 year of operation, the telescope shocked scientists with its unprecedented ability to peer into the universe's distant past. The JWST's groundbreaking capabilities have revealed galaxies that date back to such an ancient period that they challenge our current understanding of the universe's origins. This discovery has sparked widespread debate about the possibility of pre-Big Bang matter. A significant breakthrough came when cosmologist Rohan Natu, analyzing data from the telescope, identified a galaxy that existed shortly after the Big Bang, marking it as the most distant galaxy observed so far. This revelation sent shockwaves through the scientific community, highlighting the remarkable capabilities of the James Webb Space Telescope. The immense potential of the JWST to reshape our perception of the universe is beginning to unfold, with significant discoveries about the universe's earliest stages. This period, approximately linked to earlier cosmic events, holds the key to understanding the formation of the first stars and galaxies. The findings from the JWST have contradicted existing theories, revealing galaxies with features that defy previous assumptions. This surge in the discovery of early galaxies has sparked a frenzy of scientific inquiry, compelling researchers to reconcile these new discoveries with established theories. As scientists delve deeper into these findings, they are confronted with fundamental questions about the very nature of the universe and the forces that shaped its evolution. Despite its undeniable advantages, the JWST is strategically positioned 1.5 million kilometers away from Earth, protected from interference and maintained at nearly absolute zero by its sunshield, which is the size of a tennis court. This positioning allows the telescope to capture unobstructed observations of the universe, free from Earth's atmosphere. Equipped with a massive primary mirror and sophisticated instruments, the JWST was specifically designed to reveal details about the early universe that were previously unattainable. This early cosmic era, referred to as the Cosmic Dawn, began approximately 200 to 300 million years after the Big Bang, marking the moment when the first stars and galaxies started to form. The mechanisms behind this process remain a crucial area of study, with various theories exploring the roles of dark matter, dark energy, and the interactions between gas and dust and star formation. The JWST's ability to observe galaxies from this critical period presents a unique opportunity for cosmologists to test their existing models of the universe. By studying these ancient galaxies, scientists can either validate current theories or uncover gaps in their understanding that could lead to groundbreaking discoveries. Initially, the JWST was expected to detect only a few small galaxies during its early observations. However, the results far exceeded these expectations. The telescope's first images of the distant universe revealed a stunning number of galaxies of varying ages, sizes, and luminosities, far surpassing previous predictions. This unexpected influx of early galaxies has triggered a race among astronomers to reassess the record for the earliest known massive systems. New discoveries are continually emerging, leaving even seasoned scientists in awe. Following the JWST's revelations, both experts and the general public have been eager to explore the characteristics of these highly evolved early galaxies. Some theorists have suggested that potential errors in how the telescope interprets large-scale observations could account for some of these extraordinary findings. However, the general consensus remains that these discoveries represent a paradigm shift in our understanding of the early universe, offering a fascinating glimpse into how much more we have yet to learn. The newfound galaxies, made visible by the JWST, have raised significant questions about the nature of the universe, challenging traditional cosmological models. While some researchers are investigating whether these discoveries can be integrated into existing theories, others suggest that they may point to a far more complex and enigmatic universe than previously imagined. The fundamental question that remains is how the universe we know today emerged from the chaotic turmoil of its earliest stages. The JWST's early findings could dramatically reshape our understanding of the Big Bang and provide new insights not only into distant galaxies and ancient cosmic structures but also into the very composition of our own Milky Way galaxy. As Mark McFadden, senior scientist for science and exploration at the European Space Agency, aptly put it, "You build these machines not to confirm theories but to break them. You simply have no idea how it will break." The origins of the JWST trace back to 1985 at the Space Telescope Science Institute, STSCI, long before the launch of the Hubble Space Telescope. At that time, Garth Weir, then director of STSCI, was tasked with envisioning what would come after Hubble. Despite early skepticism, Weir and a small team began laying the groundwork for what would eventually become the James Webb Space Telescope. Unlike Hubble, which primarily observes visible light, the JWST was designed to see in the infrared spectrum, allowing it to peer deeper into the universe. This infrared capability is crucial for studying distant galaxies, whose light has been stretched into the infrared due to the expansion of the universe, making them invisible to telescopes like Hubble. With its massive, cold, star-like mirror, the JWST has become a key instrument in unlocking the mysteries of the cosmic dawn. The need for such a telescope became evident in 1995, when Hubble's deep field observation revealed countless galaxies in what was previously considered an empty region of the sky. This discovery demonstrated the richness of the early universe and underscored the necessity for a more powerful telescope capable of observing even deeper into space. After decades of development and an investment of approximately $1 billion, the JWST was launched on December 25, 2021. By July 2022, it was ready to begin its critical year of scientific observations. Programs such as the Early Release Science (ERS) and the General Observing Program were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded projections. The JWST's observations have already begun challenging existing models of the early universe, uncovering galaxies that defy conventional cosmological assumptions. These unprecedented discoveries highlight the importance of pushing the boundaries of scientific exploration and demonstrate the astonishing capabilities of advanced technologies like the James Webb Space Telescope. As experts continue analyzing the data from the JWST, new insights may emerge that further challenge and expand our understanding of the universe. When the first data from the JWST began arriving, cosmologists eagerly awaited the results, knowing that the telescope had the potential to revolutionize our view of the cosmos. Gone through years setting up their information examination frameworks for this moment, as opposed to following the customary peer review process, which can require months, specialists chose to share their discoveries on preprint servers, for example AR14, where papers can be freely accessed prior to going through peer review. This approach allowed for fast feedback and discussions through online platforms like Twitter, where established researchers could quickly engage in exchanges about the findings. Rohan Natu referred to this new process as science by public statement, and the resulting wave of discussion was both intense and unprecedented. However, concerns emerged about the possible downsides of this rapid dissemination of results. Claus Pontypool, a JWST project researcher at STSCI, warned that while the quick sharing of discoveries enabled rapid communication and discussion, it also risked overwhelming the scientific process. The accelerated spread of discoveries, particularly in such a monumental mission, introduced challenges to traditional scientific workflows. Despite the rapid pace of data release, the general consensus among most specialists is that the current theory explaining the origins of the universe remains central to understanding the early stages of cosmic history. This hypothesis posits the formation of stars, planets, and ultimately life, including human existence, as a crucial part of the universe's development. Regardless of its peculiar name, the Big Bang theory provides a logical explanation of the universe's beginnings. In its earliest stages, the universe existed as an extraordinarily dense point, far smaller than the tip of a pin, filled with tightly packed particles. From this incredibly compact state, a massive release of matter and energy, known as the Big Bang, unleashed the forces that would shape the universe. This colossal event, occurring billions of years ago, set the stage for the universe's unfolding story. As scientific knowledge advances, however, inconsistencies have emerged, challenging long-held assumptions. When NASA launched the James Webb Space Telescope, JWST, the most advanced and largest space observatory ever built, expectations were high that its observations would confirm the Big Bang theory. Yet, within just 1 year of operation, the telescope astonished scientists with its extraordinary ability to peer far back into the universe's past. JWST's remarkable capabilities have revealed galaxies dating back to an era so ancient that they compel scientists to rethink our understanding of cosmic formation. This discovery has sparked discussions about the possibility of pre-Big Bang matter. A significant breakthrough occurred when cosmologist Rohan Natu, analyzing data from the telescope, discovered a galaxy that formed shortly after the Big Bang, marking it as the most distant galaxy observed to date. This revelation sent shockwaves through the scientific community, highlighting JWST's unprecedented power to expand our understanding of the universe. The immense potential of JWST to reshape our perspective on the cosmos is beginning to unfold, offering profound insights into the earliest moments of cosmic history. This period, which aligns loosely with previous cosmological theories, is crucial for comprehending the origins of the first stars and galaxies. JWST's discoveries have defied established models, revealing galaxies with characteristics that surpass previous expectations. This unexpected surge of early galaxies has prompted a wave of scientific investigation, pushing researchers to reconcile these new findings with existing theories. As scientists continue to examine these discoveries, they face fundamental questions about the very nature of the universe and the forces that guided its evolution. Beyond its groundbreaking scientific contributions, JWST's strategic positioning, 1.5 million kilometers from Earth, shielded from interference and cooled nearly to absolute zero by its sunshield, provides a unique advantage. This placement allows the telescope to capture detailed observations of the universe without being affected by Earth's atmosphere. Equipped with a massive primary mirror and advanced instruments, JWST was specifically designed to capture unprecedented details about the early universe that were previously impossible to detect. This early period in cosmic history, known as the Cosmic Dawn, occurred approximately 200 to 300 million years after the Big Bang and marks the formation of the first stars and galaxies. The mechanisms driving this process remain a subject of intense research, with various theories proposing the roles of dark matter, dark energy, and interactions between gas and dust in star formation. JWST's ability to observe galaxies from this critical time offers cosmologists a unique opportunity to test their models of the universe's early stages. By studying these ancient galaxies, scientists have the chance to either validate existing theories or uncover new gaps in our knowledge that could lead to groundbreaking discoveries. When JWST first began its observations, it was expected to detect only a few faint, small galaxies. However, the results far exceeded these predictions. The telescope's first images revealed a stunning abundance of galaxies, with varying ages, sizes, and luminosities, far beyond what was anticipated. This unexpected influx of early galaxies has triggered a race among astronomers to rethink the timeline of the earliest massive galaxies. New discoveries are being made constantly, leaving even the most experienced scientists in awe. Both researchers and the public have become increasingly focused on the advanced nature of these early galaxies. While some scientists have proposed that JWST's interpretation of large-scale observations could explain these surprising results, the prevailing view is that these findings represent a significant shift in how we understand the early universe. This offers an exciting glimpse into the potential for future breakthroughs. The recent discoveries made by JWST have raised critical questions about the nature of the universe, challenging long-held assumptions in cosmological theory. While some experts are working to integrate these findings into existing models, Others suggest they may be the first hints of a far more complex and mysterious universe than previously imagined. The key question remains: how did the universe, as we know it, emerge from the chaotic and turbulent conditions of its early stages? JWST's initial discoveries could fundamentally reshape our understanding of the Big Bang, providing new insights not only into distant galaxies and ancient cosmic structures but also into the very nature of our own Milky Way galaxy. As Mark McFadden, senior scientist for science and exploration at the European Space Agency, stated, "You build these machines not to confirm theories, but to break them. You simply have no idea how it will break." The origins of JWST date back to 1985 when the Space Telescope Science Institute, STSCI, began laying the groundwork for a successor to the Hubble Space Telescope. At the time, G. Weir, the head of STSCI, was tasked with envisioning what would follow Hubble. Despite initial skepticism, Weir and a small team began planning what would eventually become the James Webb Space Telescope. Unlike Hubble, which primarily observes visible light, JWST was specifically designed to see in the infrared spectrum, allowing it to probe deeper into the universe. This infrared capability is crucial for studying distant galaxies, whose light has been stretched into the infrared by the expansion of the universe, making them invisible to telescopes like Hubble. With its massive, cold, star-like mirror, JWST has become an invaluable tool for unraveling the mysteries of the cosmic dawn. The need for such a telescope became clear in 1995, when Hubble's deep field observation revealed thousands of galaxies in a region of the sky previously thought to be empty. This discovery highlighted the richness of the early universe and underscored the necessity for a more powerful telescope capable of probing even deeper. After decades of development and an investment of approximately $10 billion, JWST was successfully launched on December 25, 2021. By July 2022, it was ready to begin its most critical year of scientific observations. Programs like the Early Release Science (ERS) initiatives and general observing programs were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded projections. JWST's observations have already begun challenging existing models of the early universe, revealing galaxies that defy traditional cosmological assumptions. These groundbreaking discoveries highlight the importance of pushing the boundaries of scientific exploration and demonstrate the extraordinary capabilities of cutting-edge technologies like the James Webb Space Telescope. As researchers continue analyzing JWST's data, new insights may emerge that will expand and refine our understanding of the universe. When the first data started arriving from JWST, cosmologists eagerly awaited the results. Many had spent years preparing their data analysis systems for this very moment.